Hey everybody, welcome to Number Theory Lecture 14. We've got some good stuff coming up here. Before we get to the new stuff, let me just mention a corollary that for some reason or other I think I omitted in the last video. It's not anything of earth-shaking significance. It's one of those things that when we see it stated, we go, yeah, okay, that makes sense. But anyway, here it is. If P is prime and P divides the product of Q1, Q2, Qn, where Qi is prime for I equal 1, 2, n, then P equals one of those prime factors. So let's look and see what it says again. If P is prime and P divides the product of primes, then P actually equals one of those primes. That's what it says. So if a prime number divides the product of primes, that prime number has to equal one of those primes. And let's prove this. It's not difficult. As is usually the case, I start off by hitting the chicken switch, and I say, let the hypothesis be given, because when I start out, I usually don't have any idea how the proof is going to go. So let the hypothesis be given. Suppose that P, Q1, Q2, Qn are all prime, and that P divides the product of Q1, Q2, Qn. By a previous corollary, P has to divide one of these factors. The corollary said something to the effect that if P divides a product, then P divides one of the factors of that product. So if P divides A1 times A2 times A sub n, then P has to divide one of those factors. So by a previous corollary, since P divides this product, the product of primes, by a previous corollary, P has to divide one of those factors. P divides Q sub I, where Q sub I is one of these primes. Well, Q sub I is prime, so it has exactly two distinct positive divisors, 1 and Q sub I. And this tells us that P is a divisor of Q sub I. Q sub I has two distinct positive divisors, 1 and Q sub I, and P has to be one of those divisors. So P is either 1 or P is Q sub I. Since P is prime, P can't be 1. A prime number has to be at least as great as 2. A prime number can't be 1. So, since P is prime, P is not 1, here's the only other alternative. P is equal to Q sub I. So again, our lemma says, is this a lemma or a corollary? A corollary. Our corollary says if P divides the product of primes, then P equals one of those primes. That may come in handy. Now, let's get on to something that's really, really neat. It's not deep math, but it's very useful math. Here's what we're going to look at. The Sieve of Eratosthenes. And what is this? It's a convenient method of generating a list of prime numbers. Now, what is a sieve? I think we know what a sieve is. It's a filter that allows water and mud and whatever to pass through, but it retains the gold nuggets. By analogy, the Sieve of Eratosthenes is a filter that allows composite numbers to pass through, but it retains the primes, the gold nuggets. And let me tell you a little bit about Eratosthenes, just a little bit. He was one of the famous mathematicians of antiquity. He was the head of the library in Alexandria, Egypt, which was probably the Harvard and MIT of its day, 20-some centuries ago. He was the head of that institute. He was a Renaissance man about 15 centuries or so before the Renaissance actually came. He was a Renaissance man in the same that, yes, he was a mathematician. He was also a geographer. He was also a musician and a poet and a historian and a number of other things, and excelled at all of them. And I guess that's why they put him at the head of the library in Alexandria. The Ptolemies, the ruling dynasty in Egypt at that time, paid the scholars of the world, the genuine scholars of the world, handsomely to relocate in Alexandria, Virginia, for the purpose of doing research. And about the only thing that they had to do was give one public lecture annually. They got a very generous stipend for living there. Any study materials or research materials they wanted, Ptolemy got. He had scouts scavenging and scouring the known world for manuscripts, scholarly manuscripts, and if they couldn't get them, if they weren't for sale, they'd get copies, so that these people, the genuine scholars of the world, could have all the research material that they needed at their fingertips. Plus, they were in the company of all of their fellow scholars, and no doubt they brainstormed off of each other. About the only famous scholar of antiquity who may not have been there would have been, let's see, the guy that lived in Sicily, and now I can't even think of his name, Archimedes. Now, he may have been there, but didn't take up permanent residence there for sure. And I don't really know if it's known for certain if he was ever there, but if he was not, he was probably the only great math science scholar, literary scholar, historian, geographer of his time who wasn't at the library in Alexandria. All of the others gladly came and were supported very well by the Ptolemies. And for about 200 years, that library really produced a quantum leap in scholarly activities of all kinds, the likes of which really has only been seen one other time in history, and that was like maybe 1600s to the 1800s sometime. So this guy was a known scholar, a Renaissance man, and he was a mathematician, but didn't really get the respect that he probably deserved at that time. You've heard the expression alpha male. Well, his fellow mathematicians referred to him as beta, in very much the same sense that alpha would have been top dog. They referred to him as beta, saying, no, you're not the top dog by any stretch. You're a second string mathematician, which is probably unfair. A lot of his critics and ridiculers and so forth, those people who didn't give him that much respect, we don't even really know who most of them were now. They faded into anonymity, and whatever contributions to math and science they made know about, or at least we don't attribute to them. Whereas Eratosthenes, on the other hand, made several contributions to math, science, as well as and geography, as well as other areas. And this is one of them. And perhaps maybe what Eratosthenes lacked in pure mathematical genius, he made up for as far as creativity goes. Plus the fact that he was an interdisciplinary scholar, and sometimes his innovations came about because of the fact that he excelled in two or more areas, and those innovations essentially resulted from him having one foot in one area and the other foot in another area. So anyway, we're going to see the Sieve of Eratosthenes, a rather ingenious way of generating a list of primes. If we had to write a computer program from scratch to generate a list of primes from 2 to 10 to the 20th power or whatever, this would be the way to go. And it would probably not be that difficult to write a program that did exactly what this algorithm shows us to do. Okay, here we go. Sieve of Eratosthenes. The first thing that we do is we create a table from 1 to however high we want to go. I'm going to stop at 100 here because I got tired of writing numbers, and also I'm at the bottom of my whiteboard, so I can't go any farther. It's probably a good idea to lay the table out as I did here, where we go 1 to 10 in the first row, 11 to 20 in the second, so that the rightmost column is just multiples of 10. Now, we're looking for prime numbers. The first thing that I'm going to do is I'm going to erase this guy, because 1 is neither prime nor composite. As a matter of fact, when most people create the Sieve of Eratosthenes, they just leave this thing blank. Now, here's the strategy. We look at 2, which is the first prime, and we reason this way. Every multiple of 2, other than the fundamental, this is 1 times 2, it's prime. Every non-trivial positive multiple of 2 is equal to a prime or a composite times 2. That being the case, every non-trivial multiple of 2, every non-trivial positive multiple of 2 is a composite. 2 times 2 is 4, that's composite. 2 times 3 is 6, that's composite. 2 times anything greater than 1 is composite. So all of the multiples on this table, other than the primary multiple, which I circled, is composite. So you know what? We don't need to check those out because we know they're composite. And look at all of the numbers in this row. They're all even, multiples of 2. We can just get rid of them. Look at all of the numbers in this row. They're all even. We can get rid of them. All multiples of 2, we can get rid of them. Look at all of the numbers in this row. They're all multiples of 2. We can get rid of these guys too. You see that? All of these composite numbers just slipping right through the sieve. All of the numbers in this row, multiples of 2, they're not prime. We let them go. all of the numbers in this row, they're all multiples of 2, and none of them are the primary multiple of 2. So we let them fall right through the sieve. We just got rid of all the non-trivial, non-fundamental multiples of 2. Son of a gun, there's only 50 candidates for prime number left. The next number remaining is going to be prime. It's 3. We circle it. And you know what? Oh, by the way, if you're not doing this on a whiteboard, you're doing it on paper, circle the primes in red, and the composites just cross out like that. This is the fundamental multiple of 3, 1 times 3, it's prime. All multiples of 3 other than this multiple are composite. We don't need them. So let's see. 3, 6 we already got rid of. 9 is a multiple of 3, get rid of it. 12 we got rid of. 15 is a multiple of 3. 18 is a multiple of 3, we got rid of it. 21 is a multiple of 3. 24, 27, 30, we got rid of it. 33 is a multiple of 3. 36 is a multiple of 3, we got rid of it. 39, we got rid of it. Let's see. 42, we got rid of it. 45, 48, we got rid of it. 51, 54, we got rid of it. 57, 60, we got rid of it. 63 is a multiple of 3, we got rid of it. 66, we got rid of it. 69, we get rid of that. 72, we got rid of it. 75 is a multiple of 3, we get rid of that. 78, we got rid of it. 81, we got to get rid of that. 84, we got rid of it. 87, got to get rid of that. 90, we got rid of that. 93 is a multiple of 3, got to get rid of that. 96 is a multiple of 3, we already got rid of that. 99 is a multiple of 3, got to get rid of that. Okay. Those numbers that are remaining are the primes or composites that are not multiples of 2 and 3. The next number on the list, 5, is prime. It's a fundamental prime, 1 times 5. We're going to get rid of all the multiples of 5 except the fundamental multiple. For example, 5, 15, 25, 35, 40, 45, 55, 65, 85, 95. I've got to get rid of all of those. And let's see, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. We already got rid of those. Okay, we already got rid of the multiples of 2, 3, and 5, other than the fundamental multiples, which we circled. Now 7. Oh, by the way, you're going to notice here that the first multiple of 7 that's not prime is going to be 7 squared. All of the other multiples of 7, other than the fundamental multiple, were already eliminated because they were multiples of 2 or 3 or 5 times 7. See, 2 times 7 is 14, we got rid of that. 3 times 7 is 21, we got rid of that. 5 times 7 is 35, we got rid of that. 6 times 7 is 42. We got rid of that. See, we got rid of all of the multiples of 7 less than 7 squared. Okay. So let's see, 7 times 8, 56, we got rid of that. 7 times 9, 63, we got rid of that. 7 times 10, 70, we got rid of that. 7 times 11, why is this one, whoops. You know what? I just circled 49 and I should, that's not a prime, it's not a fundamental multiple of a prime. This is just one that we had to eliminate. The next multiple of 7 that we have to eliminate is 77. And it makes me wonder, well, how did this multiple of 7 survive when all of the others didn't? 49 survived because it was not a multiple of any of the previous primes. 77 survived because it was not a multiple of any of the previous primes, but it's a multiple of 7 and this thing, which is prime. Okay, 77 is not prime, it's 7 times 11, we get rid of it. Okay, 7 times 12, that's 84. 7 times 13, ooh, 13's prime. 7 times 13 is 91. Okay. Got to get rid of that. And 7 times 14 is greater than 100, so it's not on here. Now, we probably didn't notice what was going on when we eliminated multiples of 3 and 5, but when it came to 7, it just hit us right between the eyes. Well, wait a minute, the only multiple, the first multiple of 7 that's left is 7 squared. It's because all of the other multiples of 7 less than 7 squared were also multiples of these other primes, and they'd already been eliminated. And then after that, the only multiple on here, let's see, we had 7 times 11. That was a multiple of 7 and a prime greater than 7. And then 91, that was still here because it was a multiple of 7 and another prime greater than 7. So let's see if we can sort of use this observation to figure out what's going to happen with our next prime, 11. And let's say (11) times any of these primes has already been eliminated. The smallest multiple of 11 that will be on this list is going to be 11 squared. Oops, that's greater than 100. There are no multiples 11 on this list. The smallest multiple of 11 that hasn't already been eliminated is 11 squared. Likewise, the smallest multiple of 13 that hasn't already been eliminated is 13 squared. The smallest multiple of 17 that hasn't been eliminated is going to be 17 squared. up to 100, the smallest multiples of 11 that haven't been eliminated are not on this list because the smallest multiple of 11 that hasn't been eliminated is 11 squared. This list only went up to 100. The smallest multiple of 13 that hasn't been eliminated is 13 squared. No, that's not right. The smallest multiple of 13 that hasn't been eliminated is 11 times 13, but that's not on this list. The bottom line is that once we get to the first number whose square is larger than the largest number on the original list, everything starting at this number and beyond is prime. Now, let me just say, just so that we get the full notion of what I'm talking about, suppose this list hadn't stopped at 100. Suppose that this list had gone to 200. Well, then guess what? When we came to 11, we'd say, you know what, 11 squared, that's 121. And way down here at 121, we get rid of that. And then the next smallest multiple of 11 that wouldn't have been eliminated would have been 11 times 13, whatever that is, let's see. 143, is that what it is? Forgive me for a minute. Okay. So the next smallest multiple that wouldn't have been eliminated would have been 11 times 13, which would be 143. And no. Let's see. Two times 5 times 11 would have been 110. We would have to eliminate that already, also. And then let's see, 11 times 13, we'd have to eliminate that. And then 3 times 5 is 15 times 11. So that would be what, 165? We'd have to eliminate that. So if this list went to 200, we would have multiples of 11 that we'd have to eliminate. 11 times 11, 11 times 13, 2 times 5 times 11, 110. 3 times 5, 15 times 11. That would be, what, 165? And let's see. See, 14 times 11. That would be what, 154? We'd have to eliminate that. But you know what? If we had a table that went to 200, all of the multiples of 2 would already have been eliminated. All the multiples of 3 would already have been eliminated. All the multiples of 5 and 7 would already have been eliminated. So when we got to 11, we'd have to look at 11 squared. And 11 times 13. and 11 times 17, we'd have to get rid of those. And then we have to look at 13 and get rid of 13 squared. And then let's see, 13 times 17, what is that, 190? We'd have to get rid of that. And that would be the end of it. And then when we got to 17, 17 times 17 is greater than 200. Once we got to 17 and found a number whose square was greater than the largest number on the list, we'd realize that every number beyond that is already prime. So I did give you some misinformation originally. Let's just look at what we have again. We eliminated all the multiples of 2. We eliminated all the multiples of 3. And by the way, once we eliminated all the multiples of 2, what was the largest multiple of 3 other than 3 itself that wasn't on the list? Oh, sorry. What was the largest multiple of 3 other than 3 itself that was still on the list? It wasn't 6 because we eliminated 6 as a multiple of 2. It was 9. So once we got rid of all the multiples of 2, the smallest multiple of 3 that we had to eliminate that was still on the list was 3 squared. And we eliminated the multiples of 3. When we got to 5, what was the smallest multiple of 5 other than 5 itself that was still on the list? It wasn't 10 because that's a multiple of 2. It wasn't 15 because that's a multiple of 3. It wasn't 20 because that's a multiple of 2. It was 25. So when we came to eliminate multiples of 5, the smallest multiple of 5 that was still on the list, 5 squared. So when we get up to the larger numbers, just remember, the smallest multiple of a prime that hasn't already been eliminated is going to be that prime squared. So when we got to 7, the first multiple of 7 that we eliminated was 7 squared, 49. And the only multiples of 7 that were left besides 7 squared were 7 times larger primes, like 7 times 11. 77, we had to eliminate that. Or 7 times 13. 91, we had to eliminate that. When it came to 7 times 17, that's a larger number than the largest number that was on this list, 100. So we didn't have to worry about that anymore. Once we get to a prime whose square is larger than the largest number on the original list, the original list went from 1 to 100. Once we get to a number whose square is larger than the largest number on the list, every number after that remaining on the list is already prime. We don't have to check anything anymore. Maybe I can say that a little bit better. If we're looking for multiples of a prime to eliminate, the first number on the list that we're going to eliminate is going to be the square of that prime, which in this case was 4. Okay. We got rid of all the multiples of 2 other than the fundamental prime itself. Let's look at 3. The first number remaining on the list that we have to eliminate as a multiple of 3 is 3 squared, 9. So we get rid of all the multiples of 3. We go to the next prime, 5. We're getting rid of all the multiples of 5 except for the fundamental prime itself. The first multiple of 5 that still remains on the list is 5 squared, 25. We get rid of that. 7, the first multiple of 7 that we have to eliminate, the first multiple of 7 that's still on the list is 7 squared, or 49. We get to 11. The first number on the list that's a multiple of 11 that's still on the list, well, let's see. It should be 11 squared, but whoops, that's bigger than 100, and 100 was the largest number on our original list. There's nothing to eliminate after this point. And all of these other numbers that are remaining on the list are going to be prime. And why is that? Well, if they're not prime, then they have to have a factor less than the number itself. They have to have a prime factor less than the number itself, which means 2, 3, 5, or 7, but we've already gotten rid of those. So once we get to a prime number whose square is larger than the largest number on the original list, that prime and all the other numbers that are still remaining on the list are prime numbers. We have no more numbers to eliminate. Okay, I made a list of all the primes between 2 and 100. We've got all of the primes less than 100. And we might think, well, you know, is that really all that useful? It is in this sense. Remember, we had a theorem that said if a number is composite, then it has a prime factor less than or equal to its own square root. We've got all the primes here that are less than 100. So let's see, what is 100 squared? 100 squared is 10,000, right? So any composite number less than 10,000, any composite number less than or equal to 10,000 has to have a prime factor less than its own square root, less than or equal to its own square root. Well, square root of 10,000 is 100. So any composite number less than or equal to 100 has to have, any composite number less than or equal to 10,000 has to have a prime factor less than or equal to its own square root, which is going to be less than or equal to the square root of 10,000, which is 100. So any composite number less than or equal to 10,000 has a prime factor less than or equal to 100. As a matter of fact, it has a prime factor less than or equal to 97. So if we just had a calculator and we were trying to test large numbers as to their primeness, any number less than or equal to 10,000, these are all the candidates for prime factors. If the number doesn't have a prime factor on this list, and it's less than or equal to 10,000, then that number is prime. If the number less than or equal to 10,000 is composite, then it's going to have a factor, it's going to have a prime factor that's on this list. For example, 551. Is it prime or composite? If we have a calculator, what we can do is just take in the candidates less than or equal to this thing's square root. And let's say, square root of 400 is 20. The square root of 576 is 24 squared, isn't it? So if we don't hit a factor, a prime factor, by the time we get to 23, this thing's prime. So there aren't many candidates to check out. Do I need to check out 2? No, this isn't an even number. We know 2 is not a factor. Do we need to check out 3 as a factor? We don't. There's a trick. If we don't know it, we'll learn it in this class. If we add up the digits of a number and the sum of the digits isn't divisible by 3, then the number is not divisible by 3 either. We add up these digits, 5 plus 5 plus 1, we get 11. 11's not divisible by 3, so this thing's not divisible by 3 either. And what about 5? No, we don't have to worry about that. Any multiple of 5 ends in a 0 or a 5. So I guess the first number to test would be 7. Does 7 divide 551? 551 is equal to 7 times, if we check it out, 78 plus a remainder of 5. Okay, 7 doesn't work. Let's try 11. 11 divides 551. Let's see. 551 equals 11 times 50. That gives us 550 plus a remainder of 1. No, 11's not a divisor. Okay, let's try 13. Does 13 divide 551? $551 equals 13 times, if we do the math, it's 42, plus a remainder of 5. And we're getting close to 23 already. Let's see, 17, is that a divisor of 551? If we divide 551 by 17, our calculator tells us that we get 32 plus a remainder of 7. 19, is that a divisor of 551? If we divide 551 by 19, our calculator says that we get 29. No remainder. So the Sieve of Eratosthenes gives us a way of generating prime numbers. And we have this theorem that tells us that if a number is composite, it has to have a prime factor less than or equal to its own square root. We generated all the primes less than 100, which means that if a number is less than 10,000 and it's composite, it has to have one of these prime numbers as one of its factors. So any number less than or equal to 10,000 would be pretty easy to check for being prime, just based on the list that we were able to generate here, the primes less than or equal to 100. This is one of the fringe benefits of us taking the course. We get to prove things like this, and the proofs are not extremely inaccessible, just the opposite, especially this one. This is a classic theorem. There are infinitely many prime numbers. That's an astounding result. And yet the proof is a pretty elementary proof, accessible by all of us. The proof is fairly straightforward. It's an ingenious proof, but fairly straightforward. And it proves an astounding result. We actually know for a fact that there are infinitely many prime numbers. So let's get on with it. It is a proof by contradiction, by the way. Okay, here's how we do our proof. It's a proof by contradiction. So we're going to make something go wrong. And if there are not infinitely many primes, there are only finitely many primes, then we can list them. Piece of 1, piece of 2, piece of 3, piece of n. If it will make us feel better, we can also assume that each prime is less than its successor. So P1 is the smallest prime, P2 is the next smallest prime, and so forth and so on. Now, it is a proof by contradiction. So somehow we've got to make things go wrong. Consider the number natural number, capital P, which is the product of all of the primes. Since there are only finitely many primes, we can do this. Capital P is the product of all the primes plus 1. Okay? The fundamental theorem of arithmetic, P must have at least one prime factor or divisor. Well, wait a minute. By our hypothesis, these are all of the primes that exist. So that prime factor must be one of these n factors. And we'll call it P sub I. Capital P, this number, has to have at least one prime factor. And it has to come from this set of prime numbers. So we'll call it P sub I, whatever that prime factor is. Now, this prime number has to divide this product of primes because it is one of the factors here. As a matter of fact, maybe I should make that a little bit more obvious. P sub I is one of these prime numbers. And so P sub I has to divide the product of all of these prime numbers. Okay. So let's see where we're at now. P sub I divides capital P, this thing, and P sub I divides P1 times P2 dot 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 Pn. P sub I divides both of those. So isn't it true that P sub I will also divide every linear combination of P and this product here? P sub I divides this, P sub I divides that. So P sub I will divide every linear combination of those two things. Well, wait a minute now. What is P? What is capital P? It's just this thing plus 1, right? This thing is equal to 1. Son of a gun. P sub I divides 1. How is that possible? Well, if P sub I divides 1, that means that P sub I is equal to plus or minus 1. And we're assuming that P sub I is positive. But anyway, if P sub I is equal to plus or minus 1, this contradicts the fact that P sub I is prime. A prime number has to be greater than 1. It has to be greater than or equal to 2. So let's summarize what just happened here. The fact that P sub I is equal to plus or minus 1 contradicts the fact that P is prime. Well, how did we come upon this contradiction in the first place? Here's how, and we state it formally. Since the assumption that there are only finitely many primes leads to a contradiction, the assumption must be false. The assumption that there are only finitely many primes leads to a contradiction. That assumption has to be false. Hence, there are infinitely many primes end of proof. And that's a great proof to know. It's well within our grasp, and the result is a huge result. With absolute certainty, we know that there are infinitely many primes. And what's more, it's well within our grasp to prove it. This should be one of those proofs that we know. Hey everybody, now that we did a very nice proof establishing that there are infinitely many prime numbers, we'd like to look at some related facts. I've written down the first prime numbers that we got from the Sieve of Eratosthenes. These are all of the primes less than or equal to 100. And if we count them up, there are 25 of them. Of the first 100 natural numbers, 25 are prime. And we might wonder if that proportion or ratio continues as we get higher and higher up into the natural numbers. And the answer is no. Prime numbers essentially get less and less dense in the set of natural numbers. Yet at the same time, there are infinitely many prime numbers. We might also look at some of the groupings of these things. 2, of course, is the only even prime number. 3, 5, 7, 3 consecutive prime numbers. That's worthy of note. We call this set of prime numbers, 3, 5, 7, a prime triple. And a prime triple is 3 consecutive prime numbers. And maybe I shouldn't use this term. Maybe I shouldn't use this term. Now that I think of it. But these are 3 consecutive odd numbers. Three consecutive odds. All prime. We're not going to waste our time looking for any more of these. This is the only time that it happens in the entire set of real numbers, entire set of natural numbers. We're not going to find another triple, 3 consecutive odd numbers that are all prime. As a matter of fact, we've had at least one problem, maybe more than one exercise, carefully disguised not to look identical, but they're actually the same exercise, plus 2, n plus 4, that's always going to be divisible by 3. Now in this case, n plus 2, n plus 4. N is divisible by 3, but it is a prime number. It is the prime number 3. For any other set of numbers, n plus 2, n plus 4, where n is not equal to 3, and n is odd, one of these three is going to be divisible by 3, and none of these numbers are going to be identically equal to 3. So at least one of these is going to be a composite. This is the only case where we have 3 consecutive odds and they're all prime. Any other trio of 3 consecutive odd numbers is going to have one of those odd numbers being divisible by 3, and the odd number that's divisible by 3 won't be equal to 3. It will be composite. So this is the only case where we can have 3 consecutive odd numbers, all of which are prime. Now I started to call it a prime triple, a prime triple, but I think that term is reserved for something else. So we've noticed 4 prime numbers grouped very close together, 3 of which constitute 3 consecutive odds, all of which are prime. But let's look at something else now. 3 and 5, and also 5 and 7. Consecutive odd numbers, both of which are prime. You know what? It happens again right here. 2 consecutive primes, both of which, 2 consecutive odd numbers, both of which are prime. Yeah, let's, happens here too. 17 and 19, 2 consecutive odd numbers, both of which are prime. 29 and 31, it happens again. Is it going to happen anymore? Let's see, 37, 41, 43. 2 consecutive odd numbers, both of which are prime. 45, 47, 53, 59, 61. 2 consecutive odd numbers that are both prime. 67, 71, 71, 73. Consecutive odd numbers, both of which are prime. 79, 83, 89, 97. Okay. What should we call these things? Each of these pairs is called a twin prime pair. 3 and 5, they're a twin prime pair. 5 and 7, twin prime pair. 11, 13, they're a twin prime pair, and so forth and so on. Between 1 and 100, there are 1, 2, 3, 4, 5, 6, 7, 8 twin prime pairs between 1 and 100. Huh. Now, for short, number theorists will refer to a twin prime pair as being twin primes. And when they say twin primes, everybody knows what they're talking about. Two consecutive odd numbers, both of which are prime. And there are 8 of these pairs between between 1 and 100. Now we might wonder if, like prime numbers themselves, they become more and more scarce as we move up into the larger natural numbers. The answer is yes. And so we might wonder, well, we know there are infinitely many prime numbers, but are there also infinitely many of these twin prime pairs? The answer is, we don't know. We don't know. This has been one of the holy grails of number theory, a problem that number theorists have wrestled with for centuries. Some of the biggest names in mathematics have invested a sizable portion of their career and lives in trying to establish one way or another whether there are infinitely many twin prime pairs or not. We even have a name for this. The twin prime conjecture states there are infinitely many twin primes or twin prime pairs, but it's a conjecture. We don't know. We don't know if there are infinitely many or not. This is one of the biggest problems that number theorists are working on. And let's see if I can get any more information on this twin prime conjecture. Every year or so, a number theorist will come up with a new king of the mountain, so to speak, a new largest twin prime pair. And I don't know what it is currently, but I'm going to find out right now. Okay, the largest set of twin primes ever found as of August 2022, the largest twin prime pair is this number, 2699686303485 times 2 to the power of 1,290,000 plus or minus 1. So in other words, if you take this number and subtract 1, you get the first of the twin prime pair. If you take this same number and add 1 to it, you get the larger number of the twin prime pair. So take this number, add 1, and subtract 1, and you get the largest known pair of twin primes. The decimal expansion of these numbers is 388,342 digits. That's in base 10. So in other words, the number of digits is greater than 308, greater than 10 to the power of 388,341 digits. These two twin primes, take this number, subtract 1, take this number, add 1, you get the largest pair of twin primes that we know of. These twin primes are greater than that number, 10 to the power of 388, 341. It has this many digits. Okay. So in other words, they're greater than that number. How do we put that in perspective? Let me correct this. It has this many digits. It's greater than or equal to 10 to the power of this number. I don't know what I was thinking. But again, let me put this in perspective. The largest twin primes have this many digits, so they're greater than that number. It is estimated that the number of atoms in the known universe is between 10 to the 78th power and 10 to the 82nd power. Number of atoms in the known universe. This is the number of digits that our largest twin primes have. Oh my goodness. This is unimaginably larger than the number of atoms in the known universe. We're talking huge, huge, huge numbers here. If the twin prime conjecture is true, and the majority of number theorists believe that the twin prime conjecture is true, if the twin prime conjecture is true, then no matter how high up we go in the natural numbers, there will always be twin primes that are larger. No matter how high up we go in the natural numbers, we'll always be able to find a pair of primes just 2 units apart. That's interesting. And yet, you know, something that's almost the exact opposite is true at the same time. And this is, you'll like this. This is essentially saying that no matter how high up we go in the natural numbers, we'll always be able to find a pair that's just 2 units apart. And we think, well, you know, primes have to be fairly close together then. Twin primes and prime numbers in general have to be fairly close together if it turns out to be true that we can always find a pair of twin primes, no matter how high up we go in the natural numbers. We can always find 2 prime numbers just 2 units apart. And yet, the opposite is also true. As we go higher and higher into the natural numbers, we can find a stretch of natural numbers arbitrarily long in which there are no primes. And I'll say that again. No matter how high up, we can go high up enough into the natural numbers that we can find a stretch of composite numbers that's arbitrarily long. And when I say a stretch of consecutive composite numbers, I mean prime number here, a whole bunch of composite numbers, and then the next prime number here. So take any number as large as you want, any natural number as large as you want, and we can find that a consecutive string of composites that long, which means that during that stretch of composites, there's no natural numbers. So as we go higher and higher up into the natural numbers, stretches where we don't have any primes become arbitrarily long as well. And I'll formalize that in a statement. Look at this. This is a pretty bold statement, and yet it's got an incredibly simple proof. Simple, but really, really clever. You're going to like this. Arbitrarily large gaps can occur between consecutive prime numbers. Another way of saying that is, given a natural number n, there exist n consecutive composite numbers. There exist n consecutive composite numbers. So let's say we have the greatest prime number less than this, and then the next prime number here's a piece of k. The largest prime number less than this number. The next prime number, piece of k plus 1, we won't find until we go through all of these composite numbers. Now let's see. Are there composite numbers? Are these all composite numbers? Let's see. Let's look at this one. N plus 1 factorial is the product of all positive integers less than or equal to n plus 1. So 2 is a factor here. 2 is a factor here. So 2 is a factor of this whole thing. Now let's look at this one. N plus 1 factorial. 3 is a factor of that. 3 is a factor of this, so 3 is a factor of this whole thing. Similarly, 4 is a factor of this thing. And what about this one? N plus 1 is a factor of this, n plus 1 is a factor of that. So n plus 1 is a factor of the sum of those two things. And notice, each of these numbers is just one larger than its predecessor. To get this number, we took that number and added 1. To get this number, we took that number and added 1. So each number in this sequence is exactly 1 greater than its predecessor. This is a consecutive string or sequence of composite numbers. And how many do we have? Well, here's our first, 1 less than that number. Here's our second, 1 less than that number. Here's our third, 1 less than that number. Here's our nth, 1 less than that number. This is a sequence of n composite numbers. So let's say that n was equal to 1,000,000. then this would be a sequence of a million consecutive composite numbers. So we would travel through more than a million composite numbers before we'd encounter a prime going from the kth prime to the k plus first prime. If p sub k is the largest prime less than this string, and p sub k plus 1 is the next largest prime, and n is a million, we're going to travel through a string or a sequence of 11, a sequence of a million consecutive composite numbers. So as we go way up into the natural numbers, prime numbers can occur, consecutive prime numbers can occur arbitrarily far apart. And yet, most number theorists believe that the twin prime conjecture is true and that there are infinitely many twin prime pairs. No matter how high up we go into the natural numbers, pick a natural number as large as you want. The twin prime conjecture says that you're going to find a twin prime pair greater than that natural number. And yet, on the other hand, we can go through a million consecutive composite numbers. This sort of suggests that primes really become more and more scarce. Not just twin primes, but primes themselves become more and more scarce the higher up we go into the natural numbers. And yet, we keep finding larger and larger twin prime pairs. The one that I showed you, what was it, 378, 10 to the, I don't know how many. It was some huge number of digits. And we say, okay, that's a big number. But we don't really realize how big it is until we compare it to the number of atoms in the known universe. And then we realize, okay, those twin primes are huge. And it also means that we've gone way, way up into the set of natural numbers, and we continue to find twin prime pairs. Excuse me. So, yeah, the twin prime conjecture has been maybe the holy grail of number theory for maybe a few centuries now. There are other major problems too, but that's one that may date back to antiquity, and we still have not solved that. And, you know, we have something like this that shows us that the higher up we go into the natural numbers, the more scarce prime numbers become. And yet we keep finding these twin prime pairs that are orders and orders and orders and orders of magnitude larger than the number of atoms in the known universe. So it's not implausible that there are infinitely many twin prime pairs. Interesting stuff.